Those pictures and concepts should seem very familiar. So what does it mean to have a buffer? Well, the buffer solution is created if we do something like this. Instead of having just the weak acid or just the weak base and letting them set up their own equilibriums, we actually start with both of them. You can see the definition below. A buffer solution is a solution containing appreciable amounts of both the weak acid and the conjugate base. And the word appreciable is kind of important too, because if I were to back up here, you could argue that this original weak acid solution does contain both. There is some HB and some B minus in this beaker, but the amount of HB is considered far greater than the amount of B minus. And same thing is true for this situation. You could say, well, here's a combination. Here's B minus combined in the same beaker with HB. But when the substance sets up its own equilibrium, again, the amounts are not really very equal to each other. The B minus concentration would be significantly larger than the HB concentration because this was B minus setting up its own equilibrium. This was HB setting up its own equilibrium. And what we're talking about here is combining the two, putting them both into the same beaker and figuring out what's going to happen. So that's probably the big question. What is going to happen if I put both my HB substance and my B minus substance together in the same beaker? So just to put some numbers to it, let's say we're going to do this. We're going to put 0.1 mole of the HB and 0.1 mole of the NAB, and we're going to stir that together into 1 liter of water. So perhaps they might step forward to agree, here's the behavior equation for the weak acid HB. And this is slightly different than the original situation because now you can see on my ICE chart I have a starting amount of both HB and B minus. So maybe the HB says, okay, I'm the weak acid, I'm going to do my behavior equation, and I am going to break up partially. Some of the HBs are going to dissociate. And so a little bit of the HB concentration will go away and a little bit of B minus concentration will appear. Maybe that's what happens. On the other hand, we could say no, B minus says no, I'm the weak base, I'm going to do my behavior equation. And I'm going to create some additional HB. So the question really, you can see down here, what does happen? Is it the HB that controls this situation, or is it the B minus? Notice in both situations here I've got to show the fact that there's a starting amount of both substances. Basically what happens here is that the HB and the B minus agree to be in equilibrium with each other, and one of these two things will take place. Either the HB behavior equation will happen, or the B minus equation behavior equation will take place. One of those two things will happen. The good thing about it is that in terms of mathematics, we really don't have to worry too much about which one does actually happen. Suffice it to say that the concentration of HB is going to change a little bit. It'll either go down or it'll go up. And the same thing is true of B minus. The concentration of B minus will change a little bit depending on which of these behavior equations actually wins. But you can see down here by the last column, the good news is we don't really have to care which behavior equation wins, because what we're going to do mathematically is we're going to assume that while both of these concentrations will change a little bit, something will happen to change them. By the time it's all said and done, they're going to end up about where they were in the first place. That's the long story. When you make a buffer mixture like this one, you can always work on the assumption that the starting amount of HB and the starting amount of B minus, even though they do change slightly, they don't change very much. So we're going to just use these original amounts as our final amounts. And what that means is that HB and B minus will set up an equilibrium with each other, and they will create a solution that contains some H3O plus and some OH minus, and everything will work out. And what we'll see, I'm going to have a problem up on the screen here for you in just a second, is that the HB and the B minus are setting up an equilibrium with each other, and that equilibrium, you can calculate it using either the Ka number for HB, or you can calculate it using the Kb number for the weak base. We'll show in just a second that it really doesn't matter which equilibrium value you use. You can use the Ka value of HB or the Kb value of B minus. Now what I've got going on underneath here is just a little bit of algebra. Normally when we make a solution, we are most interested in figuring out something about the pH of the solution, which means we either want to know something about the amount of H3O plus that's in the solution, or we want to know something about the amount of OH minus that's in the solution. This particular solution will end up with both. It's going to have a certain amount of H3O plus, it's going to have a certain amount of OH minus. It's going to be determined by an equilibrium between the B minus and the HB, but it just works out mathematically that you can use either one of these equations to figure out the final equilibrium. We'll see that in just a second. The equations that are listed in red here are, believe it or not, these are related to the equation just above. This equation is essentially a log version of the one right above it. And then so is this equation, because as you know, what is pH? It's the negative log of H3O plus. What is pKa? It's the negative log of Ka. So these two equations in red are simply mathematically related to the ones just above them. I have them highlighted in red, however, because these are equations that are given on the AP test, and the red equations, both of them originally come from the Ka and the Kb definition, but they do provide these two equations, and you'll see that it's convenient to think of these red equations as our buffer equations. Now, how would this work? Well, let's go back and actually work out the problem for a particular weak acid and base. And by the way, the last little topic here, you'll see that this is significant. Notice that both of these red equations really contain what we might refer to as a ratio. The ratio of the B minus to the HB, or the ratio of the HB to the B minus. And as it says down here, since it is a ratio form, you can actually use molarities, concentrations, or simply you can use the moles of each substance. And we'll see that happening when we work our problem.